Hello, I will start by explaining the program and how to use it to physically manipulate quaternions. A quaternion is an object in four-dimensional space with specific properties. You can learn about these properties either in the article linked in the description or elsewhere. I will be discussing the GUI step by step. First, a little teaser. What awaits those who watch the video to the end? This few will understand quaternions better. They will be able to use spatial imagination to visualize quaternions. Moreover, they will be able to use their understanding of quaternions to improve their spatial imagination. Ferris Klein has a good quote about the need to complement our spatial imagination with algebraic calculations and vice versa. And this video will help with it. There will be also a very specific practical outcome. If you need to know the result of two consecutive rotations in space around certain axes at certain angles, then after watching this video, you will be able to quickly estimate where the resulting axis of rotating will be. Unfortunately, I can't say the same about the angle of rotation. Well, that's what we have. So, let's start with the left panel. At the top, there is formula of a unit quaternion in general form. It includes the angle phi0 plus a time-dependent term, but we will consider t as 0 almost everywhere, so we are left only with angle under the sine and cosine functions. I added time for convenience. I conducted experiments and observed how things would look. You might also find it interesting to look at this when you understand what can be done with it. This formula also has components of the directional vector multiplied by the sine of the angle. Color options are options for displaying graphical elements, their color and opacity. You can explore them independently. Next is the field for time t. You can change it to alter the overall angle, but as I said, it will almost be 0 for us. Then there is a block for the first quaternion. This is the field for entering the angle phi0. This is the field for entering the frequency. But of course, if time t is 0, this member is 0 as well. And next is components of the directional vector. They are not normalized here, just for convenience, but when it recalculated in formula for quaternion, they are normalized automatically. Next, you can see the formula for quaternion with specific directional vector and frequency. But first time t is in general form, but then all parameters are substituted into the quaternion. Next, you can see the same for the second quaternion. The same phi, frequency, and components of directional vector. And here we can see the result of multiplying those two vectors. It's q1 multiple q2. I denote the scalar part of the quaternion as w. Sometimes it's written at the beginning, sometimes at the end, and sometimes it's denoted by another letter. What's the relation of these parameters to the other windows on the screen? Let's look on the left top window. Here, on the top panel, there is an exclusive view flag. I will set it so the window is larger now. Let's see what we have here. We see a coordinate system which can be rotated, scaled, and switched to orthogonal or orthographic projection. There are also three colored axes with large dots and small dots. These axes define the directional vectors for the quaternions. Their display can be turned off. I will leave only the display of the first quaternion for now. To take a closer look at it, the large ball shows the XYZ coordinates corresponding to the first quaternion. In this case, it's 0.19, 0.38, and 0.57. Let's now change the phi angle. Remember that this angle is not one of the angles you can find in the somewhere in the three-dimensional coordinate system, but the angle under the cosine, sine, and cosine. That is, if the directional vector remains the same, the change in the phi angle will move the quaternion in three-dimensional space along the axis defined by its directional vector. Let's see. We see only XYZ coordinates, but we can also look at the value of the force coordinates W. Let's exit the exclusive mode for this and look at the bottom right window. There are two-dimensional coordinate system on it. In this case, we're interested in two top graphs. On them, you can see the values of the components of the first quaternion in two planes, z, w, and x, y. But these are coordinates in a specially chosen coordinate system, where the axis of the first quaternion is directed along the z-axis, instead looking straight at the viewer. Therefore, the x and y coordinates of the first quaternion in this coordinate system are always zero. And if you change the angle of the first quaternion, only z and w coordinates, see here on this point, will change. And obviously, the green dot will move in a circle here. The red dot here represents the resulting quaternion, and its display cannot be turned off. The two lower graphs display the projections of the second and resulting quaternions in a coordinate system where the axis of the second quaternion is oriented along that axis. Let's return to exclusive mode again. There are also these small dots. They mark the boundaries of the three-dimensional unit sphere. You can look at this sphere, you can check it, and we can orient this sphere to see that those points are actually the intersection of the x directional line and three-dimensional sphere. Also, you can change the directional components, the components of directional vector. And we'll see that the directional vector will change. So we turned off a sphere, it's not need anymore. And now I am going to show the other two quaternions, second and result quaternion. And everything is exactly the same with them. That is, for the second quaternion, you can change the angle and you can change the directional vector and its components. Okay, now let's exit the exclusive mode and look at the remaining two windows. They display the same picture, but in different coordinate systems. In the right top window, a coordinate system is chosen in which the first quaternion is green, is oriented to look directly at the viewer. Let's change the angle of the first quaternion and see that in the image, the axis of the green quaternion is not visible as it's covered by its point. If you change the angle of a second quaternion, you will see that it moves along its axis. In the left bottom window, we can see the same. But here the coordinate system is chosen so that the axis of the second quaternion is facing us. If desired, the coordinate system in each window can be changed. You can even choose a coordinate system in which the axis of the resulting quaternion faces the viewer. But this system did not prove itself, and I will return everything as it was. Now let's move on to quaternion multiplication. Let's set some parameters to everything is clear visible. What is happening here? We are multiplying the first quaternion, green, by the second, blue, and obtaining the red quaternion. Of course, there are also scalar parts which are not visible on this drawing, but we can imagine them. We can move each of the quaternion along its axis and see what happens to the result. Let's also see what happens when the directional vectors change. If you just look, it seems like there are no particular patterns, but the situation will change if we start displaying certain cylinders. What are these cylinders? Let's see. Let's look at the green cylinder. How is it constructed? We take the axis of the first quaternion, green, and the distance from the second quaternion to the axis, directional vector of the first, will be the radius of the green cylinder. The same is done for the second, blue quaternion. Its axis is taken, and the distance from the first quaternion to the axis of the second, and this will be the radius of the second cylinder. Now, the wonderful thing is that the result quaternion, red, always lies on the surface of one cylinder and on the surface of the other. So, it lies on each of them, therefore, on the line of their intersection. Let's change the angle of the first quaternion. We will see that the radius of the blue cylinder changes because the blue stays in place and the green moves. Accordingly, the distance from the green quaternion to the axis of the blue one changes. But the resulting quaternion continues to be located at the intersection of these two cylinders. The same thing will happen if you change the angle of the second quaternion. Now the radius of the first cylinder, green, will change, but the resulting quaternion will still lie on the surface of both and therefore on the line of their intersection. Now it's a good time to change t, because when we change it, the radius of both cylinders will change. Both original quaternions will move along their axis, but the resulting quaternion, red, will still be located somewhere on the line of their intersection, of the line of intersection of two those cylinders. Let's take a closer look at what happens when the angle changes. I temporarily removed the cylinders, but will enable another options. Trace. It's tracking. That is, the resulting quaternion, it's red, will leave a trail behind it. Now, let's do this. We will fix the second quaternion, blue, and the first one will move along its axis. We will change an x, an angle, and we will see what happens to the result. The second quaternion is the blue point, and the resulting quaternion moves away and approaches it. Now, let's turn off tracking and see what we got. We see that the trail looks very much like an ellipse, and it seems that the trajectory of the resulting quaternion lies within some plane and does not go beyond its limits. We also know that, in addition, the result also lies on some cylinders. Now let's turn off the cylinders and look at them. It's quite clear that this white trail lies on the surface of the green cylinder. So the moment of the resulting quaternion occurs within some plane. The resulting quaternion does not leave this plane. The plane intersects with the cylinder, and the intersection of the cylinder with the plane gives an ellipse. Now let's clear the trace and change the angle of another quaternion. And look, now the resulting quaternion describes an ellipse on the surface of the blue cylinder, meaning again the trail is located within some plane, and this plane, when intersecting with the blue cylinder, gives an ellipse. Here we have such as a direct physical phenomenon, and we need to explain it. Now, let's start to explain how it turns out that when changing the angle of one of the quaternion, the result lies within a certain plane. We will perform the calculation not manually, but using the Python package for symbolic computations. I have prepared a simple notebook, and I won't even post it on GitHub. You can repeat everything just from the screen. Let's execute the cells. The first is imports, and the second is defining symbols. We will use them next. And now we have to switch on the coordinate system in which second quaternion lies on the x zeta, and the first quaternion has x part 0. Let's switch to the program, and I will set the second quaternion on the x z, and the first quaternion has x part 0. Now let's set trace flag and change the angle of the first quaternion and see what happens to the result. As we already found out, this will be an ellipse lying in a plane, and look what happens if we project this trail onto the xy plane. This trail will be projected onto some straight line. Let's see. So, if you take a plane built on the axis of the original quaternions, blue and green, then the plane of the ellipse turns out to be rotated relative to this original plane around the blue axis for some angle. And this is clearly visible on this picture. We will explain it as well. Let's switch to the Python window and show the original quaternions and their products in components. First quaternion, second quaternion, and their multiplication. And now I want to see this x and y component of the result. And the angle phi second is not changed, so it's constant. And x and y has the same part beta 1 sinus phi 1. So if the angle phi 1 is changed, x and y will be changed as well. And x and y are differ only on some coefficient. So x and y will be lie on the same line. That is, the projection of the resulting quaternion on the plane xy will lie on a straight line. That is, the resulting quaternion lies in a plane that is perpendicular to the xy plane. Consequently, the plane in which the result lies is obtained from the original one by rotating around the axis of the second quaternion by some angle. And it is obvious from this formula that this angle is phi 2. So it's angle that is set by the second quaternion. As it's quite easy to lose track of the thought here, let's repeat once again what we have done. We switched to a coordinate system in which the second quaternion, blue, is directed along the z-axis, and the first quaternion, green, has a zero x component. Such a coordinate system can always be chosen. We choose this coordinate system for convenience, which consists of the fact that in such a coordinate system, it's easier to see what happens to the original plane stretched along the blue and green axis. Let's change the first angle. What do we see? We see that the trace lies in a plane perpendicular to the xy plane, and it goes through the z-axis is as the axis of the second quaternion, and it's visible that the resulting plane is rotated at a certain angle around this axis, which is precisely set by the second quaternion. Now, if the multiplication is indeed reciprocal, meaning we can look at the quaternion product as, as the action of the first quaternion from the left on the second, or as the action of the second quaternion from the right on the first, then if we change not the first angle but the second, something similar should happen. That is, according to the assumption, a rotation should also occur, but around a different axis, not around the blue one, but around the green one. Let's check. We will clear the trace and now change the second angle. And let's first look at the forming plane and then see if it really seems like this is a rotation of the original plane around the green axis. Yes, the green axis did not change when we changed the angle of the second quaternion. Well, yes, it seems that this original plane is rotated by the angle set by the first quaternion. We can also do it differently. Choose a small angle and see that the result plane rotates only slightly relative to origin. For example, 5 degree. We can see that this rotation is very small indeed. but comparing to the first rotation, its rotation is makes in opposite direction. So, what am I leading to? Why do we even need these planes? Let's set the question this way. What is a quaternion and what does it do? We know that a quaternion describes a rotation in three-dimensional space. We have a formula for this. You can refer to the article. It defines an axis and an angle. We see the axis in the image, and here we either know the angle or can calculate it based on the position on the axis. Suppose the angle for the first quaternion, green, is 45 degrees, and for second, blue, is 60 degrees. Then, what is the multiplication of quaternions? The multiplication of quaternions results in a quaternion that represents the outcome of applying sequential rotations at certain angles around different axes. Understanding the mechanics of plane rotations, we can graphically calculate the direction of the resulting axis. What do we need to do for this? We need to construct a plane on the three-dimensional axis of the original quaternions and mentally rotate this plane around one axis by the angle set the opposite quaternion, and do exactly the same for the other axis to obtain a second plane. For example, take the blue-green plane and rotate it around the blue axis by the angle set by the green quaternion, 45 degree. Mentally fix the resulting plane. Now, rotate the same blue-green plane around the green axis now by the angle set by the blue quaternion, 60 degrees. Again, mentally fix the resulting plane. Now we know that the resulting axis will belong to both planes. That is, it will be at their intersection. To better visualize this, the program has an option to show circles. And I will see sphere as well. The circles are arcs of great circles. If you thought these were just arcs, well, that is true, but that is not what I was representing in the program. In the program, I took the original plane, green-blue, and rotated it by the necessary angle around the required axis, and then displayed the line of intersection at the plane with the sphere. And such an intersection gives the result. So the white arcs should be perceived as a result of the intersection of the rotated plane with the sphere. And by intersecting such planes, we get a straight line on which the axis of the resulting quaternion is located. A brief conclusion. So, here I've explained how you can use this program to work with quaternions, what geometric and stereographic objects emerge when working with them, the role of spheres, cylinders, and great circles. Additionally, how you can perform quaternion multiplication mentally, at least partially, to find the axis. And importantly, I hope you found aesthetic pleasure in it.